There, and I started the recording as well. So, last time, hold on, let me fix this now too. There, a little better. So, you might find yourself wanting to go to Dairy Queen after this, I don't know. All right, the Dequeue. We have that special case. So, here's where it could get funny. Paint. If it's the case where I have some, I don't know, F, which is some front, that's my null. So this is rear, right? If it's the case that I want to come along and dequeue, okay, well, I get the data out, I store it. I say front, which, okay, front was referencing that. I say, okay, front, u equal to front's next. Okay, well, that's this. And we're all set, right? And then nothing references this node anymore. Okay? We got the data out. That's what we're going to return. So if we go look at the code, that's the data, get the data. Front equals front, get next, decrease size, return to return. So in this example here, we got the data. We'll return this at the end of the function, and we update what front is referencing. Great. And now we have there's no reference variable anywhere referencing this node anymore. So it's gone, right? It effectively doesn't exist anymore for us. So now front is this one. So let's repeat the process. If I say, okay, get the data out. Okay, all right, we'll get the data out. We'll save it into data. I'm just reusing the same part of the drawing. We'll return this later. And then I say, okay, front, you aren't going to reference that anymore. You reference this. Okay, great. So there we go. Because again, nothing referenced this node right here. Nothing referenced it. So it's effectively gone. And then we decrease size, return the data. But if we have, I'm going to start over. If we have the case where I've got a single node that's referenced by both the front and the rear, right? Its next is null. So this is what our queue, our linked queue would look like if we only have one thing in it. So if we repeat the process, let's think about what happens. I take the data out. I'm storing that to return later. And then I say front, u equal front next. Okay, so you don't reference that anymore, you reference this. Which is correct because front, if it's an empty queue, front should be referencing null. But with an empty queue, rear should also be referencing null. But if you look at what we've got right here, this isn't the case. Rear is referencing this node, which is obviously no good. This is what we would call that edge case of like, well, if we're dequeuing from a queue, a linked queue of size 1, what do we want to do here? Well, yeah, we've got the special case because rear is kind of left dangling. And imagine for a second, so as far as how this should be working, this node right here should not exist anymore, right? It's sad. But if I come along and I say, oh, okay, let's in-queue. All right, well, what's in-queue look like? Well, let's go look at in-queue for a second. Well, I say, are you empty? Well, depending on how we check that. Otherwise, we say, create a new node and set rears next to in-queue and then update rear. So I say, okay, hey rear. We've got a new node over here, and your next is now this. But this is all kinds of messed up now, because this queue is supposed to be empty, yet somehow rear is referencing a node that then would be, well, we got to update rear, so rear now references this as well. So, I mean, we're in big trouble. This is supposed to be an empty queue, but there's nodes in there, and we're all kinds of messed up. This is no good. So the fix to this is what we have here. If, after we finish getting next, or removing and updating front, if it's now empty, we have to be sure to set rear to also be null. Because on a Dequeue, the only thing that gets updated in Dequeue is the front, right? Except on the special case when the rear, when it's size 1, and the rear also gets affected. In the same way with InQueue, right? InQueue, where does all that happen? Well, it always happens with the rear. It's only the rear that cares. Except on the case that when it's empty and we InQueue, we need to make sure we set front. So these are examples of edge cases. Every single time I InQueue, it only cares about the rear unless it's an empty queue. Every time I Dequeue, it only cares about the front unless it was a singleton. Unless after the Dequeue, it's now empty. Absolutely, okay. If rear is pointed to null, can rear.getNext even work? Well, rear is not pointing to null. I mean, if rear is referencing null, then rear.getNext won't work. But at no point, rear get next. We're not using rear get next. We're setting front get next, and then we just set rear to null. Maybe you could be more specific. Maybe I misunderstand your question. Oh, okay, cool. All right, good. So yeah, that's the special case. Here, okay, so if the queue is not empty, there's at least one element in it. It may be the case that both the front and rear reference the same node if there's only one thing in the queue. When looking at the code, this would result in making a new node. Okay, I'm just explaining what we already did. Dequeue and first, okay, yeah. Yada, yada. So what's the computational complexity of InQueue and Dequeue? Let's go look at our InQueue. I think I asked it here, but I never actually, maybe I didn't. What's the computational complexity of this InQueue? Look at this code for a second and think, if I have a queue of size n, how much work does this take relative to n? And I'll wait for a couple people to throw something in the chat. Nothing. I'm not seeing anything. $47. 47's correct, because 47 is effectively constant time, so it's constant time. It's not n, right? Because in queue, we just create a new node, okay. Check if it's empty, that's constant time. If it is empty, we just say, okay, front references this new thing. That's just a constant time thing. Otherwise, rear, set your next to the thing we're adding. That's constant time. And then just set rear and then update size. So it's just constant time. And then let's go look at the Dequeue. Have a look at this one. And look at this code, take a second, look at the code, and tell me, if we have a queue of size n, how much work is this going to take? 1. It's constant time. Okay, we do this, whatever, that's just a check. Get the data, that's constant time. Update what front references, that's constant time. Decrease size, constant time. Check if it's empty, constant time. Setting the rear to null, constant time. Then return the element, constant time. Everything here is constant time. So this dequeue is constant. So this is neat, right? So with our queue, a linked implementation of a queue, both the inqueues and the dequeues are constant time. Which is fantastic because I've got this large data structure that could have a billion things in it, but adding and removing from it is still constant time. So that's awesome. That's good. If, however, let's go to inqueue. If, however, I didn't have a reference to the rear, I only ever kept reference to the head, the front of the queue. So I don't have a rear reference. How much work would it take to inqueue? N. Can you tell me why it's N though? Can you explain it a little differently? Because I'm not sure that's correct. That's all you got. It depends on the length. Yeah, so that's correct, but I'm asking why does it depend on the length? Here's what I have. I have some arbitrary long linked structure. This is front. And there are n things here. So if I want to inqueue, I mean, if I come along and I inqueue, I want this to come like out. This should go here, right? So why is this order n if I only keep reference to the front? Exactly. I have to come along and be like, okay, all right, well, I'll create a new thing called like current. Start it at front and be like, okay, front, is your next null? No? Okay. Go to the next one. Is your next null? No. All right, go to the next one. Is your next null? Okay, go to the next one. And then after n times, I can go, okay, hey, current, is your next null? Oh, it is. Okay, great. Well, now current, your next is the new node. And then, yeah, there we're done. So if I don't keep reference to the rear, I need to iterate through the whole queue to find the rear node so I can just inqueue. So by just keeping reference to the rear, by having this extra field, I can now turn this inqueue, which would have to be linear, into constant time, which is fantastic. All right, unqueuing. Dequeue, variations. Okay, so a priority queue is perhaps an interesting variation on a queue. All right, so a priority queue, it's a queue, except the order that things are dequeued. With a regular queue, it's first in, first out. First come, first serve, right? So if you show up at Tim Hortons in line, if you're there first, you go first. If you're there third, you go third, assuming no one cuts or leaves the line, right? But a priority queue is a little different. Sure, we've got this idea of first in, first out, but we also have like a priority. So the things that come out of the queue, out of the priority queue, will come out based on their priority value. So think of triage at a hospital, right? If you show up to the hospital and you need stitches on your hand, and you've been there for 6 hours, right? And you're next. But then someone comes in and they fell off a ladder and cracked their skull on the sidewalk, right? Yeah, it doesn't matter that they just came in and you've been waiting 5 hours. They get to go before you because, well, they've got a higher priority in this case. So first come, first serve is a thing within the same priority, but if someone like supersedes your priority, well, they will go first. So think about how we describe what a priority queue is. Everything would be the same except dequeue. Well, I guess it depends on how you implement it. So when I dequeue, it needs to work such that when I get something out of my priority queue, it needs to not be the thing at the front, not necessarily the thing at the front. It needs to be the thing that has the next most important priority. So think about how we would go about implementing this. We have two options here. So the idea is, okay, in queue, we add something to the priority queue, and then we dequeue. We remove something from the priority queue, but the thing that comes out is the thing with the lowest priority. I hear a boop. Can you just make more than one queue? Maybe, I don't know. So let's go think about this now for a second. So every node I add, let's say, okay, 2, 3. Okay, let's say I have 3 things in my priority queue. Right? And I'm going to put, let's say lower priority is more important. So I'm just going to write the priorities here. Who cares what the data is? So this one has a priority 2. This one has a priority 7. This one has a priority 8. Okay? So if this is the case, and I dequeue, who do I dequeue? Well, the 2, which happens to be at the front. So in this case, I want to dequeue. Well, I'm lucky. It's just the first thing. But let's say I want to come along and in-queue something, a new node here, that has priority 6. Where do I put it? I mean, you can look at this and be like, well, okay, you could put it there. Or we could put it at the end, I guess. But what implication do these two different options give us? Like, what are the implications of putting it at the end versus the implications of putting it where it belongs, between the 2 and the 7? I'll let you look at that for a second and think about it. I don't want to rush you. I want to give you a moment to think about this. Let me put it this way then. If I do the in-queue where I just add to the rear, right? And let's say I have a rear reference, and this is my front. If I in-queue such that I always just add to the rear, what's the computational complexity of that in-queue? It's 1, correct? Because I just go, okay, we'll just have this go there, and this is going to be referencing that, right? Like we just move some arrows around, right? Great. But then, if that's what happens, I'm gonna hold on. If that's what happens, my queue now looks like this. Where's my thing? What did I say it was? 2. Shoot. And I had 2, 7, 8, now 6. Okay, so if I just enqueue it such that it just goes to the end, great. But now what does that mean for my dequeue? How much work is my dequeue? Yeah. So what they're saying is, okay, great. So this next time I dequeue, it's just remove the front. Well, that's easy, right? Because it's the 2. Okay, great. Yeah, so we got lucky. Now dequeue. Well, the thing that's supposed to come out is the 6. I can't just remove the front. And remember, this queue is arbitrarily long. So if I need to go find the thing with the smallest priority, and I have n things, I got to do a linear search. I got to go through and look at every single thing in that list until I find where it are in that list, in that linked series of things, until I I go all the way to the end and keep track of the smallest one I've seen so far. And then once I get to the end, I go, okay, well now I know where the smallest thing is. So there you go. You're absolutely right. So here's the thing. If we write it such that our enqueues are constant time, where we just go and we just add things to the rear, regardless of what priority they have, just add them to the rear. When it comes to a dequeue, though, it's going to be linear time because I got to go through and search the whole link structure for the smallest priority. Then I remove it. So if I have a constant time enqueue, I'm stuck with a linear time dequeue. Conversely, if I have an enqueue where I do a linear search through my structure to find where the thing goes and then add it, so that would be going back to this example, where instead here, I go through and I do a linear search to find where it would go and go, okay, it goes here. I would have to do a linear search on the enqueue to insert it, but then my dequeue is constant time because I'm guaranteed that my link structure is in order. And if it's in order, I can always just remove the front, which is awesome. So this is like there's always a trade-off. You can implement it such that you have a constant time enqueue, but then a linear time dequeue. Or you have a linear time enqueue with a constant time dequeue. There's no reason to keep track of the rear anymore, is there? Well, it depends on the implementation. Well, no, we're definitely going to at least want to keep track of the front. But if we do the implementation where we do a linear search on the enqueue, then we don't need a reference to the rear. But if we do the one where we do an enqueue on the a constant time enqueue, well, then we do want to keep reference to the rear. Is there situations where one would be better? Well, what do you think? That's a good question that I think, what do you think? Can you think of it like when would one be better than the other? If I'm going to be, let me put it this way. Can you ever have more dequeues than enqueues? Can you have more enqueues than dequeues? But, obviously they're linear time. In order to find the smallest thing in an unsorted list, I got to start at the beginning and go all the way to the end. But if I'm looking for the insertion point, I only need to go down until I find where it goes. I don't need to go all the way to the end. I don't know. These are tough questions. Right? Whoop. Only if, but that's a constant. What's a constant? I mean, the fact that it's like half? No, I know. You're right. You're right. You're absolutely right. But I'm talking about like, okay, if we were to go literally like time these things in terms of my implementation. But you're absolutely right in terms of computational complexity. The fact that like, well, on average, it's halfway down the list. So, you know, it's 1/2 of n really, but 1/2 is just a constant. So we ignore that. So it's still linear time. You're absolutely right. But we're just talking here. Assuming that's what you meant. All right. Okay, what? Okay, how? All right, well, here's where we talk. We could do the in queue. Yeah, okay. We just talked about this. Okay, cool. Now, here, let's go look at the actual implementation here. You know what? No, I'm going to open this, yes, new window. So let's look at my implementation here of a linked queue. So this is the one on the course, like the one you can download from the course website. Okay. So it's like the same, right? We've got, okay, we've got that. We've got our in queue. Here I've got some comments just to explain what's going on for you. The Dequeue first is empty size. Now, we've got our toString. At this point, we haven't been talking about the toStrings, but you should always be writing your toStrings. So this is on you. And I'm making use of this thing called a string builder. And there's an aside on this earlier in the course that if you're still stuck, you could probably go download the code for the linked queue and look at this and figure out how it works. But you're definitely going to want to write your toStrings. Now, the equals. You can go ahead and look at this, but I'm going to warn you, when it comes to checking equality on collections, things like a queue, it's nasty. And the amount of like tedium required is beyond the scope of this course. So whenever it comes to a collection, I'm going to give you these equals when I want you to have them. I'll give them to you and I'll make sure they're correct. By all means, look through the code and try to learn from it and try to get a sense of what the hell's actually going on here. But you don't need to worry about writing the equals for things like this. Now, if it's something like, if we go back to the example at the beginning of the course, we're like a friend object, right? Well, yeah, okay, write your equal for these like simple little data objects. But for something like a collection, yeah, let's not, don't worry about it. I will give them to you. And I also include this hash code. Okay, great. I think I talked about this already. I made this node class an internal private static class. Did I talk about this? I think I did, but if not, I'll say it again. Now, we wrote the node class. If we go here, yeah, right here. This is the node class. There was a topic on this, the linked structure topic, right? The links one. Here's the node class. Great. But the problem is, well, it's not a problem, but the reality is, okay, this node class, great. Okay, cool. But we've got, like, these are singly linked nodes. And then, as we just saw, there might be priority nodes. And if you go back to the linked structure, we could have been talking about doubly linked lists, right? I think we went over that, right? If we go back to previous, the queue, previous, nope, previous, there we go. Way back here. Yeah, there's nothing stopping us from having like a doubly linked list where we have like before our nodes had a reference to their next, but why can't we have a reference to the previous? You're right, we totally could do that. You could totally do this. You can make another node class that now has 3 attributes. Head. It has the data followed by next, followed by previous. So we just add a 3rd attribute that always keeps reference to the previous node. So yeah, now you don't have to worry about going, like you can go backwards and forwards. Great. A little more extra bookkeeping involved, but you know, you can make it work. So if that's the case, linked queue. Yeah, we were down here. If that's the case, when I say, okay, a node class, which one? Because there are a lot of different nodes. Is it a doubly linked list node? Is it a priority node? Is it a binary tree node? There's a lot of nodes. And node is this kind of like catch-all term we use to describe this little object that just holds on to data and has references to other things. So node is this very general term. And if I have node in my project, it can be kind of confusing, like kind of ambiguous, because you're left going like, well, what kind of node is it? I mean, you know it's a singly linked node because you only have, like you wrote it. But if someone else sees like a node class and I'm just looking here in the project, I'm going to say like, oh, what kind of node is that? And if you go here, I've got my binary node. I wrote another one called a binary node. But you know, I wouldn't call this a binary node. I just call it a node. But I had to write it binary node because, well, I already have a node class. And you can't have 2 classes with the same name. So a way around this is to say like, okay, great, we've got this node class. But instead of like having it being in the whole project, I'm going to have it exist only within the linked queue. So when I make use of nodes in my linked queue class, it goes and looks at the class, this private class that exists inside of it. If you go look at this and you look at the one node, they're identical with the exception of this is public class, this is private static class. Just some syntax stuff there. That you like boilerplate stuff you gotta write that we won't get into. But now I don't need to have a node in my whole project because it only really matters for this linked queue or linked stack. Right? But it doesn't matter for like everything else. So that's why it's like this internal class. We can do this. If you don't like this, you don't have to do it. If you do like it, cool, do it. It's just, I'm just letting you know. And let's go down here and have a look at the linked queue tests. Linked queue thorough tests. We'll look at the good one. Let's have a look. So these are the tests you can go and you can download right here. So there's the linked queue test, but I also give you like a more thorough version of the test that you can download right here. And if you do, you'll get this file. So let's have a look at the things I'm testing here. So these are my unit tests, right? And I'm going to run this just to make sure everything's working properly. Come on. Come on, where's my, there we go. Look at that, 20 tests pass, yay. So all of my tests I wrote here passed. Let's have a look. All right, so I start with the 2 fields for this test class, class under test and pre-state. So I've got this before each. Okay, before every unit test I'm going to do, I'm going to create a new linked queue and assign a class under test to it, and then pre-state assign class under test to it. I will say, even before I get to it, class under test is like a word you would like say, oh, this is the thing I'm testing. Here, this is a value I'm using to like keep track of like when before each test runs, I want class under test and pre-state to be equal. But then if I modify class under test, I want to check that, well, it's changed. I can check if it doesn't equal pre-state anymore. So FYI. So before each, we create these new queues. Great. Now, is empty returns true. So we start with these empty queues, right? So if I say class under test is empty, I better get true back. if I say class under test size, I better get 0 back. If I try to get a first, I better get no such element exception. And same with Dequeue. I better get another exception. If I do a toString, I expect to see just this boring old string that just says front, because there's nothing in there. Now I've got this other one here, when singleton. Okay, so now you'll see this is a nested class. So this is a class inside this class, which might throw you off, but if it does, just take a time to go through this on your own. It'll click. But basically what this says is, I'm saying before each, add single integer. So I'm saying class under test in queue, pre-state in queue. And you're going to say like, well, hold on, class under test and pre-state don't exist because this is a new class. Well, they do because it's a nested class. So it's kind of like this runs and then this one's nested. So then this runs. That's the fanciness of it. So it's like, okay, we do all the empty tests. Then I add single things to it and I carry on those tests. So is empty singleton returns false. Well, I better get false. Size better be 1. First, better give me the 11 because that's what I added. Singleton, oh, here we go. Singleton, if I say first on a singleton, so I do class under test first, pre-state and class under test better be the same. Meaning, remember, first doesn't remove anything from my queue. I just want to look at it. And it should be left alone. So there. Dequeue singleton returns the front. Check that it's there. Dequeue singleton results in an empty stack. So we do a dequeue. Check that it's equivalent to an empty stack, which is just a new stack. A stack. Queue. This is a bug. Someone should go and fix this. This is a bug. Someone should go fix this on the GitHub repo, or at the very least, submit an issue, because this is a bug. Okay, singleton, okay, whatever. And now we do a when many. So now this is like building off that. We did all the empty ones, then we did the singletons, and then we just add 22 and 33 to each of them. So before every single one of these tests that we're about to do, we have 2 queues that are filled with 11, 22, 33. And I carry on the tests. It's is empty better be false, its size better be correct, its in queue better work, all those things. There we go. So those are some more linked queue tests, just to go through them. Are there any questions about any of that before we jump on to the array queue, which I'm fairly certain is the next topic? Linked queue, array queue. No questions about any of that? All right. So we finished a linked queue. So before, though, we started, we had our linked stack and we had our array stack. So let's make an array queue. Why not, right? Because what do we need? Well, we need a container. So with the linked one, we had these, like the nodes, right? The linked structure. We needed a way to keep track of the front. We need a way to keep track of the end. And we need a way to keep track of the size. Great. So now we'll use an array. We'll keep track of the front and the rear. Well, we've got indexes in the array for that. And keep track of the size. Okay, whatever. So we used a link structure last time. Now let's use an array. But how? So now we're stuck to think about some implementation issues. We're stuck thinking, because there are a lot of options here. In fact, there's an infinite number of options, but I can think of 3 relatively obvious ones. At least they are to me, but maybe not to you, but that's fine. We'll talk about them and they'll probably click. So here's the first idea. We'll use an array as the container. We'll keep track of the front by always having it at index 0. And then we'll keep track of the rear index, kind of like how top is always like the end, or the top is the top of the stack, except we'll just treat that like the rear. So we're always adding at the rear, and then index 0 is always the front. And then size will always just be whatever the rear is. So I mean, here's the idea, right? Front is always this. Rear in this case is 4, right? So this is going to look very similar to the stack, the array stack. All right? So adding always happens at the end. Adding happens at the rear end. Add the element to index rear, increment rear. That's all. It's just like pushing on an array stack, right? If we dequeue, we've got a little bit more stuff going on though, right? Like if I want to dequeue from the stack, all right, well, index 0 is always the front. But then, like if I remove this, if I took this element out, copy, if I take this out, let's see if I can do this. Oh, nice. If I take this out and I have it such that, well, the front is always index 0, I've got a bit of a problem, right? Because I need to take this and go, okay, well, now you go there. I'm going to take this and you go there. Got to take this and then you go there. Got to take this and then you go there. And so on and so on and so on and so on. If I have n things in my array queue, how many things do I have to like shuffle down to fill the front back in, index 0? N, all of them. Well, okay, the in queue here is easy. The in queue is constant time. Just add it to the end, just kind of like pushing on the stack. But the dequeue here really sucks because it's suddenly constant time. And we just looked at the linked implementation, and the linked implementation's dequeue was constant time. Where, I mean, if we want to use the array one and it's linear, we're in trouble, right? Why would I ever want to do this linear time dequeue when I know I've got a simple alternative, the linked queue, that has a constant time dequeue, right? I think I may have misspoke at the beginning. The array queue's dequeue with this idea is linear time, but the linked queue is constant. So if you have a choice between constant and linear, which do you pick? Constant. There's no question. So, all right. So first of all, remember, in order for us to implement a queue, it needs to implement in queue, dequeue, first, size, and is empty. If we go and take this idea and actually go implement this array queue, like with this idea, will it be correct? Meaning, can you use this idea to implement the queue? It's not a trick question. It should be an easy answer to this one. Uh-oh. What's the problem here? Do you have a question about my question? Oh, people are just leaving. What's going on here? Okay, so the question is, we have this idea one for the queue. We talked about how we'd implement in queue, implement dequeue. And you know, if I want to go and implement a queue, I just need to implement in queue, dequeue, first is empty in size, right? So can I take this idea and build a working array queue? Exactly, right? See, it's not a trick question. Of course you can. It totally works. You add the methods. Yeah, great. And yeah, you'll need your expand capacity. You're right. So, yeah, that would totally, like, it could totally work. So there's nothing wrong with this implementation in terms of correctness. But I've got this feeling that if I can make the linked implementation have a constant time Dequeue, I feel like I should be able to have an array queue implementation that can be constant time dequeues as well. So here's another idea for our queue. Idea 2. Instead of using 0 as always the front, what we'll do is we'll keep track of the front index as well. And then the size will just be the difference between the rear and the front. So the idea now is I've got something like this. I come along and I enqueue. Well, okay, I just add the thing to rear, like the other one. But the difference will be the dequeue. Oh, another issue here. Someone can go fix, someone can go fix this. Oh my goodness. Someone can go fix this on the GitHub page. So the enqueue is the same, but the dequeue will be different. What I'll do is I will just say, okay, this index is now useless, and front is just index 1. So now next time I dequeue, I just dequeue from index 1 and then increase the front to be index 2, and so on and so on. So with this idea, the difference here is instead of front always being 0, we just keep track of front, and front can move down the array as we go. And of course, we never want front to get past rear, right? That'd be a big problem. So can we use this idea to implement a queue? We need our enqueue, our dequeue, our front, our first, size is empty. Can we do this? In expand capacity, is it worthwhile to shift the list? That's an interesting one, so that it starts at 1 again. That's a very good observation, right? Because otherwise, we're gonna kind of have this array grow really large, and we're gonna have all this empty space. And even if we don't do the expand capacity and move things back to the front, we're still gonna have that obnoxious empty space. Imagine I start with a queue of size 1 billion. I enqueue 100 things, I dequeue 100 things, I enqueue another 100 things. I've got 100 useless cells at the beginning of my array, wasting space. I can still use this implementation, and suddenly our enqueue is constant time, our dequeue is constant time, but we're wasting a lot of space. So we've made an improvement, but it's still kind of, So here's where we'll end today, and we'll pick up here Friday. But yeah, and then we'll look at idea 3, which is the good one. All right.